Okay, let's now turn our attention to the nucleophilic acyl substitution reactions. The general mechanism, the nucleophile negative electrons will attack the partial positive carbonyl carbon. The pi bond will break. Pi bond reforms, kicking off the Z group. And as we said before, the better Z it can exist on its own, the weaker it is as a base, the more likely this reaction is to occur. Good nucleophiles, our potential nucleophiles, R minus, very good nucleophile, H minus, each of these have a nice lone pair, OH minus, water is an okay nucleophile, alcohols and water. The thing to remember, if water can do it, an alcohol will probably do nearly the same thing because a pKa of water is 15.7, pKa's of alcohols are 16, maybe 18, very similar here. Acetate ion, carboxylates can be the nucleophile. Ammonia, decent nucleophile, and various amines, good nucleophiles. Note, if a nucleophile is neutral, then during a reaction, a proton is lost to give a neutral substitution product. For example, here is CH3, C double bond O, Cl, an acid chloride, acetyl chloride here. And NH3 is a neutral nucleophile. It's a decent nucleophile, but it is neutral. So the bonding, or the lone pair electrons here will attack the carbonyl carbon. The double bond will break, double bond will reform, chloride will get kicked off. We know it's a very reactive compound. But that would leave an NH3 positive on here. There'd be a positively charged nitrogen bonded to this carbon. Just do the structure, just kick off this chlorine, put on a nitrogen with 3 hydrogens, and you'll see that nitrogen is positively charged when you do formal charge. And when that happens, we say the chlorine is going to come back and take that hydrogen. Now, the truth of the situation is it's not going to be the chlorine. We'll get into the reactions. We're going to need some extra base, some extra nucleophile to take off that hydrogen because as written, this reaction pretty much goes 100% the opposite direction as written. Pretty close. So, yeah. But for, our friends at home and when we're talking about it, reactions at parties, and we don't want to get into the nasty details, we'll just say, oh, yeah, we get HCl also. Here's another example. Here, if we've got this carboxylic acid here, and we react it with an alcohol with H+, what we're going to find is if this oxygen attacks the carbonyl carbon, you'd have this oxygen now with 3 bonds to it, 1 to this hydrogen, 1 to this carbon, 1 to carbonyl carbon, and they'd be positively charged. Well, this proton here will leave, form H2O here, and we will deprotonate that nucleophile. Very important because we learned it in previous chapters, in Chapter 7. When a nucleophile attacks something, when a nucleophile attacks a carbon, the nucleophile stays together. No bonds in the nucleophile are broken. So what we find here is when the neutral nucleophile attacks, no bonds are broken but during the attack, but later when we get this nitrogen, it'll be positively charged, or this oxygen will be positively charged. If it's got a proton on it, then that proton gets taken off. A deprotonation reaction will occur. All right. Continuing on, the better the leaving group, the more reactive the RCOZ compound is. Chloride, very good leaving group. So acid chlorides are very reactive. NH2 minus, a very bad leaving group, and therefore amides are not very reactive. More reactive acyl compounds can be converted into less reactive ones using nucleophilic acyl substitution, but not usually the reverse reaction, which means I can take a very reactive acid chloride and convert it to an amide. That will go just fine. Let's see, taking an ester and converting it to this an anhydride, acetic anhydride here, and OCH3 minus, no, this isn't going to work. Anhydrides are much more reactive than esters. Recall that the reactivity goes acid chloride, anhydride, then carboxylic acids and esters, and then amides. And so this is more reactive. Anhydride is more reactive than an ester, so this reaction probably won't work. And as something we did learn from chapter 7, if Z minus, the leaving group, is a weaker base than the nucleophile, then the basicity of the nucleophile, the reaction will go. The leaving group always needs to be the weaker base than the nucleophile. All right. So let's look at our reactions going from most reactive to least reactive. And we'll start our reactions of acid chlorides, the most reactive. And when you write down the mechanism, as we saw before, when you're writing down the reaction, if HCl is formed, if you get a deprotonation and form HCl, in general, we're going to add pyridine, a weak base. This is the structure of pyridine. It's weak. It's fairly sterically hindered also. And it will react with the HCl that would have been formed to form this protonated pyridine and Cl minus. So, for example, here if we have an acid chloride plus acetate ion, it'll form the anhydride here. And that will work because anhydrides are less reactive than acid chloride. So this reaction goes just fine. Acetate ion is negatively charged, so we get Cl minus, all is good. But if we take this acid chloride and react it with an alcohol, we will form the ester. But we will need this pyridine in here in order to take off this extra electron and make this protonated pyridine chloride salt. One kind of bending the rule thing here we have that's not too bad. If we have our acid chloride and we have an amine that has a hydrogen on it, we don't have to add pyridine because we already have this basic amine in there. And so we really add two equivalents of amine in order to get this reaction to go. And here's the mechanism of how this reaction works. And we're going to use a neutral nucleophile so we can show the deprotonation. Water can come in, attack an acid chloride, attacks carbonyl carbon, the pi bond breaks to form the negatively charged beast right here, the OH2, the H2O is on there, but note that oxygen has a positive charge. Well, then a pyridine can come in and take that hydrogen to make this an OH on this time. We get this deprotonation reaction. After the deprotonation reaction, the pi bond reforms and the chloride gets kicked off. All right, and so that gives us our carboxylic acid plus the chloride plus our protonated pyridine compound. So that's the way all these mechanisms are going to work. The nucleophile attacks carbonyl carbon, breaks the pi bond. If a deprotonation reaction needs to occur, then it occurs, and then the pi bond reforms and kicks off the leaving group to give our new neutral molecule and protonated pyridine if we needed it to do the deprotonation and chloride. So let's look at these reactions now with anhydrides, the second most reactive group of RCOZ compounds. And so if we have acetic anhydride, the thing to remember is one of the carbonyls is going to get attacked, the other is part of the leaving group. So in this reaction right here, if we decided, okay, if this is the carbon that gets attacked here, then this whole thing is the leaving group. This whole beast right here is the leaving group, this carboxylate. So if we take this anhydride, acetic anhydride, and take something like salicylic acid here, this oxygen of the OH will attack this carbonyl. Note, this oxygen of the OH is more nucleophilic than any of these two oxygens out of the carboxylic acid part, because a carboxylic acid, pKa 4 to 5, OH here, pKa's, normally alcohols pKa about 16. We'll find out this is actually pKa about 10 because of the the phenolic group here, but still, this hydrogen is not as acidic as this hydrogen is, which tells us this oxygen is more basic than these oxygens. Because the weaker the acid, the stronger the conjugate base. So then the weaker, the higher the pKa of this proton, the stronger this oxygen is as a conjugate base, which also means the stronger it is as a nucleophile. So this oxygen is more nucleophilic, attacks the carbonyl carbon, the pi bond breaks, deprotonation will happen, then the pi bond will reform. Note, even though this is kind of drawn in one step, you have not leveled up, so you can do that. This is actually 3 steps here. First, this attacks and the pi bond breaks, then the deprotonation is going to occur, and then the pi bond will reform and kick off this leaving group. Long story short, this oxygen no longer has this hydrogen on it. This oxygen has the carbonyl and the CH3 on it, and we get this acetyl salicylic acid, or as you might call it, aspirin. Let's take acetic anhydride again and react it with para-aminophenol. And so our question is, we've got this oxygen here, which is nucleophilic. We've got this nitrogen here, which is nucleophilic. Which of these two is going to attack the carbonyl carbon? Well, electrons on nitrogen are more basic than electrons on oxygen. Amines are more basic than alcohols. Therefore, this lone pair here on the nitrogen is more nucleophilic. It attacks the carbonyl carbon, kicks off this leaving group. Net result, the carbonyl is now attached to this nitrogen. We have created this amide here, and this just happens to be acetaminophen. So note how nucleophilic substitution, nucleophilic acyl substitution, very important on making things that cures your headaches. So I would imagine the more you studied this, the less your head will hurt. Okay. Right. Bottom one down here, if you have an amine, note we've got a neutral amine here attacking this carbonyl carbon. We can see that we can surmise that the CH3C double bond O will be attached to this amine, but it'll be protonated. So an extra amine has to come in and deprotonate before the leaving group leaves to make this amide. Okay. We're going to end the video right here because the next thing to look at in our sequence is carboxylic acids, and they're going to give us a number of problems. So we'll look at that in the next video.